Okay, let's get a quick little sound check here. There goes the echo. Fantastic. Okay, so it's been a while since I've done one of these programming streams. I thought I should probably do another one. So today, we're going to be getting back to the wonderful world of Atari 5200 programming. So my last set of videos, we built a very simple kind of space shooter game, like a Space Invaders or Demon Attack type shooter game. And I wanted to kind of branch out and start fresh and go off in a different direction and show off a few other aspects of the 5200 and some different techniques that people use to make games for the console. And I kind of have an ulterior motive with what I want to do here because I have an idea for a game I want to do after the one I'm working on right now. But there's some testing, a little bit of proof of concept stuff I want to do surrounding that. And this project is going to be kind of in that direction. So in a way, I'm doing a little bit of this for myself, but it's also going to be a bit of an interesting ride. So if you want to see some more of the There we go. I've had a problem with this microphone just dropping from time to time. I'm glad I noticed that. Okay, so anyway, I'm sorry if that microphone was out that whole time. Hopefully you're able to follow along with what I was doing. So what I'm doing here is I'm going to create a full screen of these tiles. So here's what we're going to do. Okay, so I was going to figure out how many tiles we needed. So there are 24 rows times 40 bytes. So we got to do 960 bytes of this data. So we're going to do this. We're going to do this kind of brute force here. So here's what we're going to do. All right. We're going to set up a loop to write to address 2000, since that's where the graphics data is at. So there's our target address. And then we're going to do 24 rows. So I'm going to save 24 to FD. Stan, that's set. And then we're going to go into a loop here. So in each loop, we're going to do 40. Well, we'll start at 39 because that's an offset. Then we're going to actually, no, we need 2 loops. We'll call this outer loop. We're going to load number 1 because that's the ID. That's the tile ID. And then on the inner loop, you know what? I can do this differently. Let's put that into X. Okay, and then the inner loop, we write 0 to FE indexed by Y, decrement Y. As long as it's not minus, branch to inner loop. Once it's minus, we're at the end of the row. So we decrement X. If X now equals 0, we're done. And we're out. If X does not equal 0, we need to update the address we're going to. So we're going to load FE, clear the carry bit, add 40 to it. That takes us to the next row. Store that in FE. Then we got to, I'm just going to do, this will bring the carry over to the next byte if necessary. And then jump back to outer loop. All right, so if I did this correctly, we should get a big full screen of this stuff. Branch out of range. It's right there. Did I not tag this as subroutine or something? Is there another done in here or something? Oh, there's one way up. Oh, okay. Got some label problems here. Not even subroutine can save you from that. When you start getting label clashes like that, it's usually a sign your subroutine is too long. Okay, so if we did this right, we should have a full screen full of that pattern. And look at that, there we go. So we got that. This is a tiled pattern over the whole screen using two colors in the tile. Kind of a darker blue and a lighter blue kind of mixed together. That's kind of a nice little pattern. So now I'm going to cut an area out of the middle of it. You know what I'm going to do? I'm going to take this. I'm going to create a subroutine called build board or build screen just to get these out of here because I'm going to run into more label clashes. So let's just take, well, actually this can go away now. Well, we can get rid of this. This just gets overwritten. That does nothing. I'm going to take all this, copy it out, and put it in here. Now I don't need to call this screen done. It's just done. Well, it's background done because I'm going to do some more. In fact, we're going to need to change these loop labels too. Nice, long, descriptive label names. Background outer loop. Background inner loop. Sometimes I think this keyboard is intentionally doing stupid things. I mean, I know I'm just hitting the wrong keys, but sometimes it just doesn't feel that way. Okay, so background done. So here we're going to do a JSR to build screen. And then we'll put an RTS here just for testing purposes. I'm going to do more stuff here. Okay, we still got our background. Beautiful, beautiful. Okay, so the next thing we need to do then is to I want to kind of carve out an area in the middle. But I want to start. Okay, it's 24 rows. I want to leave 2 rows at the top and 2 rows at the bottom. So I'm going to start 2 rows in. So we're going to store so 2 rows in would be hex 2000 plus 80. So it would be I'm mixing hex and decimal here for convenience. This would probably be best to not do that, but I just don't care to do the conversions right now because I just don't. Okay, so I'm going to start. This is going to be 2 rows in. Or, no, I want to start 3 rows in. I want to leave the top 2 rows alone. So I'm going to start 2 rows in. And I'm going to do this for 20 rows. So there's my counter. And then what I'm going to do is I'm going to call board inner outer loop. We're going to do the same basic idea. What I'm going to do now is I'm going to kind of I'm going to like cut a hole in the middle of the screen. I might come back and do like a fancy border or something here, but for now we're just going to like cut a hole into the middle of it. So we're going to be putting character code 0 in there, and we're going to be doing. Okay, so if I'm going to cut, I'm going to do 10 wide out of the middle. So that's going to be, we're going to start then, if it's 40 wide and it took 10 out of the middle, that would leave 15 on each side, which means I want to start at 24, offset 24, I think. This is one of those things I just have to do and see if it comes out right. Okay, so we're going to write this to Y. Now I'm going to decrement Y, but this time we need to compare. I think I'm done at 14 if I'm doing the math right in my head. If it's not 14 yet, we just go to board inner loop. And we dex. I feel like I went too far on the other one. No. Branch on equal to board done. I like to make my labels right away, usually. Just, so I don't forget. All right, so branch on equal to board done. Otherwise, we need to, again, just move the pointer up by 40 to the next row. And again, adding 0 to bring the carry forward. All right, I'm not sure I got that right. We'll find out. It builds. That's. Look at that. That's exactly what I wanted. I don't know if that's centered or not. Actually, it's 1 row too far. I'm gonna bring that up a row. I started too deep. That's weird. Why did that end up that way? Oh, yeah, duh. I know why that worked that way. I was right the first time, and I added 80. Stupid me. There we go. Okay. This is exactly what I wanted. So, if you haven't figured it out already, maybe, I don't know. I can't tell if that's centered or not. My eyes are just not. Is that centered? I don't know. Let me try. Try changing this by 1 to see if it looks centered. If I do that, that doesn't look right to me either. All right, yeah, I'm gonna go back to what I had. We'll run with this until it's proven otherwise. Okay, but what I want to do here is kind of a, well, I was going to do Tetris because it's a very simple game to program, and it's something that we can do. It makes very good use of this mode because this mode pretty much gives us the blocks. It just kind of hands them to us. So I wanted to do Tetris, and I have some plans for a kind of like a block and pit style puzzle game for the 5200 in the future. And I wanted to just do some experimentation with some ways to approach doing that. So I thought I would take advantage of this stream and, you know, go ahead and do that with whoever's watching this, so you can see some of the techniques involved in doing that. So here's our board. We just kind of carved it out of the middle there. And we're going to do some fun with blocks. So let's try defining one of these Tetris blocks. So I haven't really planned what this is going to look like. I'm just kind of winging it here, but we can probably come up with something pretty simple. So let's have like a color around the edge, and then like a brighter color in the middle, like a darker color and then a brighter color. In fact, for the moment, let's just use the colors we already have. So which is the darker color of colors 1 and 2 here? Okay, color 1 is the darker color. So let's make something here. So we'll make the outside edge the dark color. So it'll be 1, 0, 1, 0, 1, 0, 1, 0. Now remember, pixels are about twice as wide as they are tall. So if you want the border to look close to uniform, you have to do 2 rows of it to make up for the difference in width and height. Okay. And then the bottom 2 bytes will look just like that. It's the ones in the middle that will be a little bit different. So we're going to do 1 byte dark, 2 bytes light, and then 1 byte dark. And then repeat that 3 times. So if I did this right, it should look kind of cool. We'll see what it looks like. Okay, so well, we need to just. I'm just going to drop one in just to see what it looks like. In fact, you know what? Here's what we'll do. We'll fill the whole board area with these just to see what they. Actually, it's number 2, just to see what they look like. Okay. That's that's kind of what I expected, I guess. Unfortunately, it's the same color as the outside of the board, so that's a bit of a problem. We probably want that to be a different color. But we have kind of a block, so let's make use of some different colors here. So I think since we used 2 colors for the background, which may have been a mistake. Okay, let's do this differently then. So if 1, 0 is the darker color, here's what I'm going to do. We're going to change the definition of this one here. We're going to use the background color. Because why not? We're going to use the black. We'll stipple it with black because that'll be kind of cool. So if 1, 0 is the darker color, 0, 1 is the lighter one. So we go 0, 1, 0, 0, 0, 1, 0, 0. And then the next row will be the opposite. No, 0, 0, 0, 1, 0, 0, 0, 1. And then we'll repeat that pattern 3 times. So this will get us a slightly darker background because we're going to be stippling with black. Yeah, so that's kind of a different, slightly different color background, which I'm fine with. I'm perfectly fine with that. Now, what we might do to enhance this a little bit later is create like a border tile, a set of border tiles we can put around the pit, like, just to create some sort of a visual separation there. But I've got 10 across. Great, perfect. So I got at least the width of the pit is right. So I'm pretty sure 10 by 20 is the size of a Tetris pit. If it's not, 10 by 20 is close to it. But, we're going to go with 10 by 20. All right, so we've got something to work with here. So let's go ahead and what are we going to do here? All right, let's put the pit back to black. Perfect. All right, so this is our little pit I'm going to throw stuff into. So I have programmed Tetris several times in my life. So I'm a little bit of a pro at it by now. That used to be my method for learning new programming languages, was to code Tetris in that language. So I've written Tetris many times in many languages. Oddly enough, though, I've never done it in assembly on a 5200. Although the first 5200 project I was going to do, which I completely failed at and put aside the 5200 for several years after failing it. It wasn't quite Tetris, but it was like a Tetris-based game. And sometimes I think about going back to that game. But Tetris is not that hard to code. And there's a lot of different ways you can do it. So we're gonna take this. We'll see where we can go with this. So I think the first thing we need to do then is just get some sense of how this is going to work, like as a game. So obviously we need to have a current piece. We need to know where that piece is, which effectively means which 4 blocks does it occupy, because every Tetris piece is 4 blocks. So what our current piece is going to be is 4 coordinates on that grid that are the current location of our piece. We need to be able to have that piece fall, and we need to be able to rotate it. Now, if we wanted to get fancy, we could use both controller buttons and do 2-directional rotation. So we can go this way or we can go that way. I'm not sure I'm going to get that fancy. We may just do one button and you can only rotate in one direction. I will leave 2-directional rotation as an exercise to the viewer. Maybe. That's my initial plan. So it's just kind of an idea of a rough checklist, right? We need to be able to put a piece onto the board. We need to be able to have it fall. We need to be able to rotate it. We need to be able to move it left and right. And I guess we need to be able to fast drop it. Now, fast dropping, there are a lot of different Tetris implementations do this different ways. There's some where it's like a smooth drop, where you can drop it a little bit and control it, stop partway down and control it. There's some where as soon as you hit fast drop, bam, it's down. And that's all there is to it. And of course, we also might want to do scoring. I'm not sure how much we really care about scoring here, but that is something you would want to do, in a real game. And then stuff like leveling up, counting lines and all that. So we also need to be able to detect lines and remove them. But that's not hard. That's actually pretty easy to do. So we need to be able to detect lines, remove them, shift the board down, all that good stuff. And then you want to have the next piece indicator, the next piece box. So you want to know what the next piece coming up is. And all that. There's a lot of stuff you could do. I'm not sure how much we're actually going to do. In fact, this particular episode of this is probably going to be shorter than my usual ones because I need to put a little bit of thought myself into how I want to approach doing this. I don't think I'm going to be able to wing this like I kind of did with the shooter, where I was just thinking up, well, let's do this. Because this is a much more concrete thing. Like, we know what Tetris is, right? We know what Tetris is, how it's supposed to look, how it's supposed to behave. So I can't just make stuff up with this one. But let's think about what we might do first. So the first thing that a Tetris game is going to do is, I guess, generate a piece, right? So let's go ahead and put a piece onto the screen. So what we're going to do is we're going to create a subroutine called generate new piece. Now, I do want to think ahead a little bit to the next box, because when you generate a new piece, where it actually goes is not onto the board. It goes into the next piece box. And then the next piece, the thing in the next piece box enters the board. But we can have this subroutine do both of those things because they kind of go together. I mean, they're always going to happen together, except the first time. Because you need to generate the first new piece, which is going to go up there. And then, yeah, so, well, we'll think about it. All right, so how are we going to generate a new piece? Well, there are 7 different Tetris pieces. So I think the first thing we should probably do is come up with some sort of identification for these 7 pieces. So we're going to come up with some constants here, all right? So first piece is the L piece. So we'll call it piece L. And we'll give that code, we'll say that is piece number 0. That's always the first one I think of. Then there's the reverse L piece. So piece L reverse equals 1. Then there's the, I guess you could call it the S piece, like the 1, 2, 3, 4. So we'll call that the S piece. Piece S. Almost 2. And then you have the reverse of that, which is like the Z piece. I could have called L S reverse. I'll call it Z. Equals 3. Then you have the T piece. Equals 4. Then there's the square piece. And then finally there's the straight piece. If I could spell right. Okay, so there's our 7 pieces. Now we have ID numbers for these things. So the first thing we would need to do is to select a random piece. Now, random number generation is always a tricky thing, and you can get as fancy as you want to get with this, really. So I don't think I'm going to go to the extent of creating a proper random number algorithm that's going to give a nice even distribution over 7 pieces, because that is a kind of an awkward number to work with. I think I'm just going to pull off of random and mask it down and keep picking until I get a number from 0 to 7, frankly. So the piece distribution will be slightly biased, I think, in favor of the first piece, if I remember right, but I don't really care. So the first thing you do is figure out what kind of piece we generate. So here's what we're going to do. We're going to load random, so we get a random value from Pokey, and we'll mask it down to, we're going to have to mask it down to 8. So we'll AND it. We'll leave 1 plus 2 plus 4. So mask it down to 0. No, not 0, 8. 0, 8? God, my brain is not working tonight. 1 plus 2 plus 4. 0, 7. Okay, so we'll mask it down to 7. So this gets us down to the range 0 to 7. What we want is 0 to 6. So, well, you know what? No, we won't bias it. What we'll do is we'll mask it down to this. We'll compare it to 7. And if it equals 7, we'll just pick another number. in theory, this could go for a very long time without ever picking a valid number, but the chances of that are extremely low. So that this will probably be good enough, and this should get us a reasonably even distribution. These numbers are coming out of Pokey's noise generator, so it depends on the structural details of the noise generator and how that works. But I don't know. We'll just go for it, see what happens. So this will get us a piece, and then we need to actually put that piece in. For the moment, we're going to just put the piece straight into the board. Like, we'll worry about the next box and all that stuff later. For the moment, I just want to put the piece into the board. So the way we're going to do that is, well, you know what? I'm not sure how we're going to do that. What we need to do is we need to look up in a table of some kind to get the piece layout and where it starts. So I think what we're going to do, what will we do? How will we do this? Oh, oh, hello there. Yeah, the Pokey noise generator is a shift register. I think it's a 15-bit shift register, if I remember correctly, and it exposes the lower 8 bits as a random value. So it has the funny property where because of the cycle timings, if you load from random, then immediately load random again, the upper 4 bits of your first random number will be the lower 4 bits of the second one. So it's because it will have shifted 4 cycles in that span of time. But here, especially since I'm introducing the and the comparison, that'll be enough time for the whole thing to flush through before I pull up another random number. So that will go away. But let's see, how are we going to do this? All right, so we're probably going to do here some sort of a lookup table. Now, every piece has 4 cells, 4 individual squares. So what I want is a list of these squares and where they go. But I'm not really sure how I'm going to do that. So what we will do, I think, let's see here. We'll call this piece table. I have no idea what this is going to look like right now. So I think what we need then is a set of X and Y coordinates for each piece. Now these are going to be relative to the board. So I think the top row of the board will be row 0, we'll say. And then the left column will be column 0. So for example, the first piece, I don't remember what I was using for that. I think that was the L piece. Yeah, so the L piece here. Now, there are some ways you could do this a little bit fancier. Like you could have the piece actually enter the board, so only like the bottom part of it appears first and then it kind of slides in. I don't think I'm going to go to that level of complexity. I think it's just going to plop into place. So it's going to be a little screwed up sometimes, but we'll take, this is just an example, so we'll run with that. So the L piece, what we'll do is we'll put the first, I think what we're going to have in the table, I think what we'll actually have is a series of XY coordinates. So each table entry is going to be 4 2-coordinate pairs, because that will give us the location of the 4 squares that are going to make up the piece. So I think we'll do, let's see, what will we do? So for the L piece, since it's 8 wide, if we start at 0, we'll put it at 4, 0. I could pack these into individual bytes, but let's not get fancy with it. So the first piece will be at 4, 0, then we'll be at 4, 1, then 4, 2, and then 5, 2. So that's what an L piece looks like. And I think what we'll do for now is we will force the random number generation. We'll skip that. And we'll just always do an L piece for the moment. So I'm going to comment this out and just load 0. We're going to fake it for now. And then once we have the entire table built, then we can actually kick in the random number generator and see what happens. But, so if we go down and look at the table here, each table entry is 8 bytes. So if we take the random number ID that we get from the random number generator and multiply it by 8, that will be the start of the table entry for this piece. And fortunately, 8 is a power of 2. So to multiply by 8, very easy. Just shift left 3 times. So this is multiply by 2, multiply by 4, multiply by 8. So this gets us from piece ID to table index. Then we're going to take that index and we're going to transfer it to the X register so that we can use it to index the table to pull out those pairs. So what we're going to do is we need to pull out those pairs, and then we need to somehow convert those into offsets. In fact, you know what? I'm thinking it might be easier to put the offsets into the table, because the worst case scenario is the straight piece, which is going to span 4 rows. So 4 rows of 40 bytes is 160, which is you can fit in a byte. So we could just make it a sequence of offsets. And I think that might actually be the easier way to go. So let's think about this. So where did I start the top of the pit when I drew it? I started it at address 2000, so 2000 plus 80 was the address I started at. So if we use that as the base, what does that get us? You know what, even better, let's not use that as the base. Let's use the actual start of the pit as the base. So that's going to be 2000 plus 95. So we'll do offset from the start of the pit is what we're going to do. So that'll give us only a 4-byte entry, which will save us some space. It'll be simpler, so we won't need to calculate the differences. But you know, on the other hand, we kind of need to be able to calculate the differences, I think. Who cares? We'll run with it this way. So if we call the top left cell of the board offset 0 and move over. So we'd be at 0, 1, 2, 3 would be the first block. Then the next, you know what? No, this is a bad idea. This is a bad idea. The more I think about this, the worse it gets. We're going back to the old plan. Okay. So with that in mind, then, we need a way to convert these coordinates into the actual memory location in, memory, where we need to place the cell data. So what I'm going to do then is, here's what we will do. We're going to write a new subroutine. We're going to call it cell to address. And what this is going to do is it's going to take the cell with, let's say, the, I'm going to switch this over to Y. So I'm going to take the first value that we read is the X coordinate. What did I call that table? Piece table. All right. So here's what we're going to do. We're going to load, Okay, we're going to load the first value out of the table. This is the X coordinate of the cell. So I'm going to put that, I'm going to transfer that to the X register. Actually, can I go direct X with that? I don't think I can. I always forget which I can do with all these different address modes. No, I can't go direct X with that. I have to load it into A first. All right, so this is the X coordinate of the cell that we're going to do. And then we're going to load the Y coordinate of the cell. Wait, I have to increment Y to get to the next. I mean, actually, no, I don't need increment Y. We can just do piece table plus 1. Indexed by Y. You can save a lot of time and space by indexing the base that you're going, by incrementing the base rather than the index. Okay, so this is the Y coordinate. Then we're going to jump here to cell to address. So what cell to address is going to do is it's going to take the X coordinate in X, the Y coordinate in A, and it's going to resolve those into an address that we can write to for that specific cell. And it's going to put that address in FEFF, so we can then just go right straight to it and say, that's the place. So we need to figure out how to do that. So how would we do that? Well, we need to take the base address of the board, which we don't exactly know right now, but we'll figure it out. We need to add a bunch to it. What do we need to do here? Okay, this is going to be some tricky math. I'm trying to work it out in my head right now without using a whiteboard. Okay, I got it. We need to add 40. For every Y row, we need to add 40. And then we add X. But we need to know what the base address is. I think the base address is going to be, if we took 10 out of the middle, that leaves 15 on each side. We did 2080. It's going to be 2095. So here's what we're going to do. So unfortunately, okay, we're going to have to clobber Y here. So I'm going to take, this will be my low byte, and then This is the high byte. So this is the base address of the board, give or take 1 byte. We'll figure. I may be off by a byte here. We'll figure it out. So what we need to do is the accumulator right now has the Y coordinate. So we need to multiply that by 40 and add it to this address. Now, there is no multiply instruction on this chip, so we're going to have to do this a little bit differently. But I need to use the accumulator to do the math. But on the other hand, I don't need Y anymore. So we're going to transfer this to Y. So Y now contains the Y address. So we're going to go into the Y loop. So for every row, we need to add 40. But it might be 0. If it's 0, we don't add anything. So we're going to immediately do a branch on equal to 0 test. And if it's equal 0, we go to while loop done, because we don't need to do anything in that case. So let's go ahead and put that label in. While loop done. All right, so for every time that y does not equal 0, we need to add 40 to that base address, because that gets us to the next row down in memory. So we're going to load 40, clear the carry bit, add it to FE, update FE, and then add the carry bit to FF, in effect. Okay, so we updated by 40. Then we're going to decrement Y and jump back to Y loop. So now this should get us to the right column, the right row. Then we have to add X, the value in X, to where we are now to get the right cell on that row. So once the Y loop is done, we very simply transfer X back to A, clear the carry bit, add FE, store it in FE, and then you might have had a carry, so we got to do the other byte. Okay, so I think that works. I might be off by like 1 byte or something, but I think that's going to work. Of course, we need to actually do something with this, but this will convert cell coordinates to address coordinates, I'm pretty sure. We'll find out. All right, so if we did this right, then we should now have the coordinates in FE, FY. So what we're going to do is we're just going to put like block number 1 at that location. No, number 2. That was a block. And we're just going to see what we get here. So let's go actually call generate new piece then. So board done. We have no real game logic at this point, but after build screen, we'll jump to generate new piece, and we'll see what happens. Maybe we got it, maybe we didn't. Either way, we had a plan. Right, I don't know what I just did. Unresolved symbol FE. All right, I think I just got like a stray symbol somewhere. I don't know. Oh, here we go. Got to make that hexadecimal. It has no idea what that is. Okay, so see what we get here. Look at that. That's exactly where it was supposed to be. Check that out. All right, so we got the first one. And there it is. That's the cell. That's where it shows up. So there's our L piece, or at least one block of it. I do need to get some different colors in there. But, hey, colors can come later. So we took the first entry out of the piece table and showed the second one. We need to do all 4 entries, right? Because there's four of these. So we need a counter here. Okay, so one problem here is that this cell to address like clobbers everything we're using here. So we need to organize this a little bit better. So we're going to take the index, the starting index, and we're going to save it somewhere. It's in both the accumulator and Y at this point. So you know what? I'm going to put it on the stack. So we'll save it on the stack. And then we're going to go into a... no, hold on. After we get the index, we need to do 4 blocks. So we need to go into a 4-block loop. But we also need to... we need to know how many blocks we've done. So we're going to load 4. I'm going to store that to FD, which I know doesn't get clobbered. This is where things do get a little bit trickier, because I'm trying to juggle memory locations, to make all this work. So this is going to be our tracker. So I'm going to loop 4 times, or we'll loop 3 times, I suppose, to get all the pieces. So here we go. We load piece table Y, transfer rate X, load piece table 1Y, JSR. Okay, so all right, so here's what we're going to do. This is not what I wanted, actually. This is getting a little more complicated than I thought, because this processor doesn't have enough registers to work the way I want to. So we're going to save the index to FC. I think we're going to need it. All right. So the first thing in the loop we're going to do is we're going to load the index into FC, because we're going to need it. All right, so we load that, transfer rate X, load that, JSR cell to address, get the values back, do the cell. Great. Then we're going to decrement FD. So this is our loop counter. If this equals 0, we're done. We've created the piece. If it does not equal 0, we need to go to the next piece, which means we need to increment that index twice, because we read 2 coordinates. So we're going to increment FC, and then increment FC, and then jump back to loop. Actually, you know what? I got a better idea. So as you go back to loop, we're going to load Y, FC. So we need to get the index back. And then we're just going to increment Y twice. And I think what we'll do is, like, the first thing in the loop is we'll update FC. I think this... No, this isn't any faster. Never mind. I'm trying to optimize, and I should not do that. Don't optimize. Don't be an idiot. Just increment twice and jump. This is not performance critical code here. So if this was done correctly, which maybe it was. Oh, wait, I need the done label. Okay, so if this was done correctly, we should see the entire L piece now. Look at that! It's done correctly. Okay, so we've got the table entry for our first piece. This is so much farther than I expected to get tonight. All right, and it's just after 1700. We got time. All right, so I think what we might do here, we might sketch out the table entries for all 7 pieces, so we can generate all 7 of the pieces, and that might be where we stop for tonight. But there's our L piece. All right, so let's do the next one. So I'm going to force this to a random number of 1. So we're going to get the next piece, which I believe was reverse L. Yeah, piece L reverse. So here we go. So what does the next piece look like? Well, it's going to start 1 further to the right. It's going to be 5, 0, 5, 1, 5, 2, 4, 2. So that's our reverse L piece. So we compile, run. There's our reverse L piece. Look at that. That easy. That quick. All you do is put in the table values and you go. One of the things you learn very quickly doing games for these sort of consoles, not just the 5200, but any of these old consoles, is that tables are your friend. Lookup tables save you so much time and effort, and a significant amount of ROM space is going to be eaten up by lookup tables because they just make things so easy. All right, so now we need the S piece. Now, this, I'm not sure how we want to orient this. I think we'll do it vertically. Where's my table? All right. I think I'm going to label these. Okay, so next we have the L piece, or the S piece, which is going to be, I think it's going to be 40, 4, 1, 5, 1, 5, 2, I believe. I'm going to do another pane here so I can go up here where the random pieces are being generated. Okay, so we're going to do, we'll force this to 2 now. And this should get us the S piece. There's the S piece. I call it the S piece. Yeah, I don't know what people call it. Because when you turn it this way, it looks kind of like an S, I guess. Okay, now the Z piece would be next. That'll be piece number 3. So this would be 5, 0, 5, 1, 4, 1, 4, 2, I think. There we go. There's the Z piece. No. Yeah, that's the Z piece. There's the Z piece. Excellent stuff. What's our next piece is the T piece. Now this, I have no idea how most Tetris games drop this piece in. I think I'm going to drop it in flat, like with like a table, kind of. I think is the way I'm going to do it. So I guess we'll start at, well, no, I don't like it because then I can't center it. But, on the other hand, I can't really center the, okay. We'll do it flat. We'll do it like a table. So it's going to be 4, 0, 5, 0, 6, 0, 5, 1. Put piece 5, didn't I? All right. So this should be our T piece. There it is. There's the T piece. And then we have the square piece. Always easiest to work with because it doesn't rotate. So that's an easy one. 4, 0, 5, 0, 4, 1, 5, 1. Oop. Oh, I put decimal points in there. Too much floating point number work in my PC project. Should be square piece. If I can type. Bam, there's square piece. And then finally, we're going to have straight piece. So I think this one will be 4, 0, 4, 1, 4, 2, 4, 3. Now this is one where in a fancier Tetris setup you'd want it to kind of enter the board because it takes up a lot of vertical space, right? I mean, that just sucks up a lot of space real quick. But we're not making the world's best Tetris game here. We're just playing around. We're just experimenting and seeing what we can do. So there you go. There's a straight piece. So now, just for the sake of experiment, let's try this. Let's put that random selection back in. Now, this, I don't know how this emulator starts the random number generator, so this might actually keep giving us the same piece over and over again because the timing is going to be exactly the same every time I run it. But let's see what happens. Square piece. Oh, no, it's not. Okay, so it must randomize Pokey at the outset instead of starting it at in a known state because otherwise I'd be getting the same piece every single time. But look at that. That's pretty impressive. Okay, so that's pretty darn good. Pretty darn good. Okay, so I think that what I might change some of this next session. I've got some I've just remembered a bunch of things from previous times that I've done Tetris that make things quite a bit easier. So I may alter some of this, but the basic concept is going to remain the same. But hey, let's look what we got. So I introduced you anyone following to ANTIC mode 4, which is the tiled mode, the 5-color tiled mode. Created a couple of basic tiles. We got this background tile, and the blank space is technically a tile, and our piece tile, which is right now colored too much like the background. I mean, we're going to put some different colors in there in the long run. And we got this random piece generation put together, and we have a piece table. And I think the way I did the random number generation, it should be an even distribution, or pretty close to it, because it throws away the overflow. Because if I kept the overflow and just wrapped it like did a modulus, it would favor the first piece, the L piece. And in an 8-bit random number, that is a significant bias. And you would definitely notice that. But I think the fact that we're throwing out that one result evens it out again, or at least gets it pretty close to even. It's amazing how, I've done so much computer game programming where I always heard stuff about random number bias and how, how they can affect things, how it can screw things up. It wasn't until I started playing a lot of board war games and looking at how things work in those that I really understand the mechanics of the random number bias and how that affects things. I get it now. I totally understand it now. So I look for stuff like this, but I do think this might be an unbiased random, or at least unbiased with respect to the source. I mean, I can't speak about how about and any peculiarities of Pokey's generation. But anyway, I think I might cut this off a little bit early tonight because it's been a while since I've done one of these. I wasn't super prepared for it. I wasn't really sure how far I was going to go with this. And I want to put a little bit more thought into this before next week so that I can be a little more prepared for what I want to do. But we got an excellent start here. We got some tiles. We got a board cut out. We got a piece table. We can create pieces. We got this handy function that can map coordinates to addresses in memory, which is going to be very handy. Extremely handy. And fortunately, it is going to be a tad slow, especially for addresses toward the bottom. But I don't think that's going to be too much of a problem. There's not a lot going on in Tetris. You only have one thing active at a time, which is that piece. So I don't think the performance of that mapping routine is going to be too much of a problem. There are definitely better ways that could be written. In fact, you might even justify a full lookup table for this. But especially for Tetris, right? Because you're going to have a lot of extra ROM space at Tetris, not a lot of game logic here. So having a giant lookup table to map those cell coordinates to addresses might be entirely justified for a game like this. But I don't think I'm going to go to those links. But it would be an interesting experiment and something to think about for when I actually do make a game like this for real. How do you map those cell coordinates to addresses? There's a lot of different ways you can do it. And I'll have to think about it. Because part of the reason for doing this is to prepare me for a future project I have in mind. But I do think that's probably where I'm going to cut things short for now. So next week, we will get a little deeper into this. We'll get the piece moving. I think initially we'll probably just make it fall without any control. Just get the timer in there to make it fall. Figure out what's involved in doing that. And of course, we need to track where it is. That's something we really haven't done yet. Like, we loaded it and we displayed it, but we're not tracking where it's located. We just kind of wrote it into RAM. So we're going to need some kind of tracking for where the piece actually is. We're going to need to track what its rotation state is, because if we want to rotate it, we need to know what its current orientation is so we can adjust it to its new orientation, however that works. That's something we'll need to think about. And that's especially complicated for pieces with 4 orientations. Like this piece, for example, here only has 2 orientations, so it's easy. You just flip to the other one. But we got 4 orientations, need to go to the next one in line. So we need to make sure that works. But yeah, we'll get to all of that. But yeah, so I think next week we'll start with some very basic piece movement. We'll get it falling. Now, what we could do to be super fancy here, I don't think we're going to do it because the main focus here is to work with ANTIC mode 4. But you could make the active piece a sprite. That way you can do smooth movement. Because I think we're just going to do block by block, like chunky movement with this because we're using the play field. But if you made this a sprite, you could do smooth movement. And what you would do, which is a very common technique, is it would be a sprite until it hit its position in the board, at which point it would become a you would write it into the playfield memory, and it would just become tiles at that point. And then the new sprite would be the next one. Of course, we would have to use 2 sprites here because some of these pieces are too wide when turned sideways, so we'd have to have 2 sprites to represent some of the bigger pieces. But it would certainly be doable. That's something you could do if you felt fancy. And in the game that I am going to do in the long term, I may do just that. There are some other techniques you could do too, where you could do dynamic tile generation and actually create the intermediate tiles for smooth movement. But that's a bit more complex than I want to get into here. But anyway, I keep saying I'm going to quit, and I keep not doing it. So we're going to quit right here. So next week we will pick this up and continue the odyssey of ANTIC Mode 4 and creating a very simple Tetris game. So I will see you next week.